Hello students, welcome to lecture 10 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be discussing about electromagnetic waves in periodic medium. So here is the lecture outline. We will briefly look into how electromagnetic behaves with a periodic medium where the refractive index or the permittivity periodically varies with space. And then we will go into the discussion of photonic crystals, which are also known as semiconductors of light. We will see how light propagates or wave propagates inside photonic crystal. We will have a brief discussion of the band gap structures in general, and then we will go into the discussion of photonic band gaps. We will compare photonic crystals with solid state physics, and we will also see how the wave equations look in the two cases. So, when we talk about electromagnetic waves in periodic structure, there are different type of periodicity possible in the refractive index or the dielectric properties. Okay. So, we will first look into the simplest case of this periodic variation of refractive index in the form of photonic crystal. So, here is a particular figure that shows a one dimensional photonic crystal, which is nothing but a material which is a engineered material which you can make that possesses a periodic modulation of the refractive index. So, you can see the two different colors showing you two different materials which are periodically altered. So, one can be high refractive index, another will be low. So, it is like high low high low high low and so on. So, A marks the period of this alternating high low materials, and when light will propagate through this particular periodic variation of refractive index, how that is going to affect the propagation and the confinement of light within, and this is what we will be seeing in this particular lecture. So, the photonic crystals are basically, as you can see, are periodic optical structures that are designed to affect the motion of photons in a similar way the periodicity of a semiconductor crystal affects the motion of electrons. So, that is where you can draw the analogy between semiconductor crystal, and this is also crystal for light. So, you call it as photonic crystal. So, photonic crystals, the periodicity can be along one dimension, 2 or 3. So, that way the crystals can be 1D, 2D or 3D. So, quite complicated structures can be constructed and they can give rise to many interesting properties. So, this is just for your understanding. When I say 1D variation, this is how you can see that it is periodic in one dimension. This is when the periodicity comes in the 2 dimensions. So, it is basically 2D. You can think of these are like columns of square cross section. So, the two different colors in each case tell you that you are actually having two different materials, and by convention the darker material has higher refractive index. So, you can see the variation is along 2D, and when you have the variation along all 3 axes, you call it 3D photonic crystal. So, here also we are just using different colors to tell you the different materials. So, you can also see that this can be easily fabricated. There will be some difficulty in making this one, and the 3D one is the most difficult one to fabricate, but possible. So, what we understood, that photonic crystal is defined based on its periodicity of the dielectric material, whether it is along one or more axes. So, let us take the simplest one and discuss further. So, 1D photonic crystal, that means you can simply take identical parallel planar multi-layer segments. So, you can just take stacks of those materials, high low high low high low and so on. So, these are often used as gratings, that can reflect optical waves incident at certain angles, or you can also use them as filters to selectively reflect waves of certain frequency. So what is important here to see is that you have got a periodic variation of the refractive index. So if you plot the refractive index like nx, this is along the z direction. Okay. So what you see here, it is low. When you encounter the darker medium, it is high. Again the white medium, that is low, and so on. So there is a variation, or it is toggling between n1 and n2. Okay, that is what is the refractive index of this low and the high medium, and this lambda, capital lambda, tells you about the period of the grating. Okay. So as in any normal crystal, as you can see, the photon crystals are also periodic structures. So they also have unit cells, which is basically repeated in particular direction to generate the entire lattice. Okay. So here these two things can give you the unit cell, right. So that is like the two adjacent layers can form the unit cell. So what you can do, you can just take this pair and then repeat it, okay, and the periodicity is lambda, and that can give you the whole 1D photonic crystal. Now the electromagnetic waves that encounter or interact with this kind of structure will also have a special waveform that must bear the periodicity of the structure, and these are called block waves. Okay. So let us go into the details of it. So first consider a homogeneous medium, which is basically invariant to any arbitrary translation of the coordinate system, and for this particular medium, an optical mode is nothing but a wave that is unaltered by this kind of a transition. So it changes only by multiplicative constant of unity magnitude, something like a phase factor. Okay. So you take the plane wave, okay, e to the power minus jkz, and this is particular such mode which upon translation by a distance d will become exponential minus jk. Instead of z, it will be now z plus d. So you can split them into the two fractions, right, the two exponentials. So here you can see that this particular term is basically nothing but the phase factor, right, that is introduced by this translation operation. So this phase factor exponential minus jkd becomes the eigenvalue of this translation operation. Okay. Now if you consider this 1D periodic medium, this is basically invariant to the translation by a distance capital lambda, which is nothing but the periodicity. That means for every period, whether you translate the unit cell by 1 period or 2 period or 4 periods, you will always get the same property, right. So that means the optical modes will also maintain their form upon such translation, and they will be changing only by a phase factor. So these modes will typically have this form uz or z, okay, is pkz exponential minus j capital K z. Okay. Now what is that? This particularly, it is representing a travelling wave which is going along z direction. Now this pkz is basically the amplitude function that has got the periodicity of the structure. Okay. That means this is also periodic along z with the period of capital lambda. Now these are the modes, right. Now this form basically can satisfy the condition that if you do a translation lambda, okay, that basically alters the wave only by a new phase factor, which is exponential minus j k lambda, since the periodic function is basically unaltered by this kind of translation. So the optical wave here is known as a block wave, and the parameter k that you will see, that basically specifies the mode and its associated periodic function, which is pkz, okay, that is nothing but the block wave number. So, these are important terms that you understand in a periodic structure, and that is how the electromagnetic modes evolve along a periodic structure. So, the block wave is nothing but a plane wave which is exponential minus jkz. Now, it has got a propagation constant of k, and the amplitude of that wave is basically modulated by the periodic function which is pkz, okay, and it has got the same periodicity of the structure, the lambda, okay, and that is the periodicity, right. So, this function will have the characteristic of a standing wave that you can see from the figure. So, this is how the travelling waves, the solid line looks like, and then when it goes and comes back, it can form a standing wave, okay. Here the periodicity is marked, okay. So, that is how waves behave in a periodic structure. Now, since a periodic function of period capital lambda can also be expanded in Fourier series as a superposition of the harmonic function of the form this, say you can write exponential minus j m g z or z, okay, I'll stick to z, okay, because we are also using g. So, in this case m can take any integer value, so 0 plus minus 1 plus minus 2. So, with that you can understand that g is basically, okay, the inverse of your periodicity. So, this gives you the spatial frequency, okay. So, g equals 2 pi by capital lambda. So, this is basically the spatial frequency, okay, spatial frequency. Now, you can see that the block wave is a superposition of plane waves of multiple spatial frequencies. So, it can be k plus mg, okay. So, m can be anything 0 plus minus 1 plus minus 2 and so on. So, the fundamental spatial frequency g of the structure and all its harmonics mg, when added to the block wave number k, they basically give you the spatial spectrum, okay, which is basically shown here. So, we have got this structure, we have got the wave propagating this way, there are reflections, waves coming back in this part, okay. So, there is a travelling wave, the two forward and the backward wave, okay, can form a standing wave pattern. This is the periodicity, and when you do the Fourier series of this particular periodic structure, you can find out the spatial frequency. So, this is the block wave number, and then you have plus g, minus g, the plus 2g, k plus 2g will be here, k minus 2g will be here. So, these are the different spatial frequency components for this particular structure, right. So, the two modes of the block wave numbers k and k prime, which is basically k plus g, okay, they are basically equivalent since they have the same phase factor. What will be the phase factor, as you can understand? So, here you have this phase factor will be exponential minus j k prime capital lambda, okay. So, from this equation k prime can be replaced by k plus g, so that you can split them into two exponents, okay. So, you have got this and this. So, this is nothing but 1. So, you can simply write that this and this will have the same value. So, okay. So, they are equivalent. So, it is also evident that since the factor exponential minus j g z is itself periodic and can be lumped with the periodic function p k z, right. So, for complete specification of all the modes, we only need to consider the values of k which are lying within this particular interval, that is within g, okay. So, you do not need to go beyond that, because the things are repeating after that, right. So, you should only consider the values of k in the spatial frequency interval of width g. This much is enough, and g is nothing but 2 pi by capital lambda. So, you can only consider the interval from symmetry. You can see you can only consider the interval of minus g by 2 to g by 2, which is basically minus pi by capital lambda comma pi by capital lambda, and that is also known by a term called the first Brillouin zone, okay, and that is commonly used construct to study this kind of periodic structure. So, what is happening within that range is repeated throughout the structure. So, that makes your life very simple to understand how waves interact with this periodic structure. So, if you consider optical waves which are inherently periodic, okay, they interact with periodic media in a unique way, particularly when the scale of the periodicity, that is the capital lambda, is of the same order of the wavelength of the incident wave. Okay. For example, spectral bands will emerge in which light waves cannot propagate through the medium without severe attenuation. Okay. So, waves with frequencies those lie within that particular forbidden band will be called the photonic band gap, and they behave in a manner which is very similar to the total internal reflection. This thing just the light is just being rejected by that medium, but one important difference with total internal reflection here will be that this rejection or the forbidden band will work for all directions. Okay. So, if you try to understand then what happens when certain frequency wave will be rejected by the crystal, that means the transmitted wave is basically getting diluted or destroyed, which is coming from the destructive interference among the waves that are scattered by different elements of this periodic structure. And here you can see an example. So, if you take a 1D periodic structure or 1D photon crystal where N1 equals 1.5, N2 equals 3.5 and the distances of the two layers are same, you can see that this is a photonic band structure where you do not see any light being allowed in this particular regime, right. So, you can calculate what is that frequency, okay. Omega b turns out to be here pi c naught by capital lambda n bar, okay, and g is you already know. So, what is n bar? N bar is basically the mean refractive index if you compute the mean of the two n1 and n2, okay. So, here also for comparison the dotted straight lines that you see here basically represent the propagation in a homogeneous medium which has got a mean refractive index of this n1 and n2. So, in that case you could calculate omega by k value simply, that is like omega b divided by g by 2, okay. This side is g by 2, you get c naught over n bar, which is also nothing but c, the speed of light. So, this is basically the light line you can say, and inside the crystal this basically bends here, okay, and it opens up a gap in this particular region, in this particular frequency, okay. So, this here is a graphic illustration of what happens if you choose the wavelength of your incident light within the photonic band gap. So, light will fall and it will get reflected, okay, from all the different interfaces. Now, if they kind of are in phase, then they will just form a standing wave, okay, within the material, and it will not allow your wave to propagate through the material, right. So, that is where the reflected waves are in phase and they are blocking the propagation of light through that particular periodic medium. Now, if you consider light which is outside this band gap, so they are basically allowed to go through the material, and how it works, you again get the reflected waves, but they are not in phase. So, they do not add up and give you a standing wave. So, this reflected wave basically just dies off and light can propagate through the crystal with slight attenuation, right. So, this band gap phenomena sounds very similar to the electromagnetic properties of crystalline solids such as semiconductors, right. So, in semiconductors we have seen that periodic wave associated with an electron can travel in a periodic crystal lattice and you will get energy band gap. So, the terminology, if you see in photonic crystal literature, is largely borrowed from the solid state physics. So, in semiconductors you have periodic array of atoms, in photonic crystals you have periodic variation of dielectric constant. So, something very similar. Here the length scale of this periodicity is in atomic level. Okay, so you can call atomic length scale because you are talking about atoms. Here the length scale is comparable to the wavelength lambda, okay, of the light that will be falling on these structures. These are natural structures and these are artificial structures or engineered structures. So, here these are controlling the electron flow. Obviously, in the photonic crystals you can control the wave propagation or EM waves propagation. So, in 1950s this electronic revolution was completely done by semiconductors, and still we are very much dependent on semiconductors for almost all our computation. So, photonic crystal also has got a lot of potential because they open up a new frontier in modern optics, right. So, if you want to see the band gap structures in general, so where the lights are not allowed to propagate through the crystal, we call them as stop bands, or they are also called band gaps. Now, you got to understand that there is a difference between a complete and directional band gap. So, complete band gap means the propagation is forbidden from all direction and for all the polarization of light or waves, okay. So, an optical emitter embedded in a 3D photonic crystal cannot radiate photons with the frequencies inside a complete band gap, right. So, this is how it should look like. So, for both the two orthogonal modes T and TM modes, there should be a band gap, and that should be for all the k vectors within your brilliance zone. That means it will take care of all the directions, okay, and for both the polarization, and that is how you get complete band gap. Now, if the propagation is forbidden for some direction, but it is allowed for some other directions or for some other polarization, we call them as incomplete band gap or directional band gap. So, we will see how that look like. So, this is one example of incomplete band gap. As you can see, this is a typical band diagram. So, these are the points. So, I will not go into complete details of how these band diagrams are calculated and all these things. If you are interested in more details of how photonic crystals, the band gaps are obtained, how do you calculate all these things, I already have a course on NPTEL on photonic crystals, fundamentals and applications. You can see a couple of lectures from those and understand how it is computed. So, here I will just briefly tell you that this is basically a square array of dielectric columns. So, this is the top view. So, they are just looking like circles. So, this marks the brilliance zone, and this is the irreducible brilliance zone, and these are the points of interest gamma x m. So, we basically march from gamma to x to m to gamma. So, this is how you take care of all the directions possible in this crystal, and this is the normalized frequency. So, it is plotted as omega a over 2 by c. You can simply write it as a by lambda as well, okay. And you compute it for T modes and TM modes. T modes are shown in red, T modes are shown in red, TM in blue. So, what you can see here, for all the angles or all the directions, the blue lines, there is a gap. So, you get a TM band gap here, okay, but however T, there is no band gap because T are merging, right. So, here are the structural parameters. As you can see, the radius is taken as 0.2 of the periodicity. So, A is basically the periodicity of the structure or the lattice, okay, and here are the parameters taken. So, the permittivity of this column was 8.9, which is for alumina, and then it is in air. Now, what is important, these are the structural parameters. As you can see here, for TM modes you see the band gap, but there is no band gap for TE modes. So, it is an incomplete band gap. Similarly, if you look for another kind of structure, which is basically a square array of dielectric veins. So, they are just connected like mesh. So, you can see the veins are having thickness of 0.165 A and made of the same material, epsilon equivalent 8.9, it's square array. So, we go with the same kind of trajectory gamma x m gamma and calculate it. What you see here is that you see a band gap opening for TM modes, there is a band gap for TE modes as well in this case, but they do not fall within the same frequency band. So, it is not a complete band gap, whereas here you can see that they overlapped for the TM and TE for all the directions and the same frequency, you get complete band gap. That means that is the difference between complete band gap and directional or incomplete band gap, right. So, these are all 2D arrays, or you can say 2D photonic crystals. So, you can think of a lattice of cylindrical inclusions again that gives you this kind of a complete band gap. That means for any direction or any polarization, light will not be allowed to enter the crystal. Now, there are some exceptions like photonic crystal fibers, in which only the propagation along the axis of the cylinders is allowed. Okay. Now, these cylinders are practically nothing but air voids in the glass fiber. So, this is where you want to make your light to propagate through the air. Okay. So, this is some kind of engineering people have used to take help of to get rid of the nonlinear effects in a optical fiber. Okay. So, in this case not only the propagation across the fiber, but also the oblique propagation should be prohibited. So, one more thing to note here is that the complete band gap, where you see as a rule it implies that the propagation is basically prohibited in the plane perpendicular to the axis, right. So, you can also take other kind of photonic crystals, something like metallic rod in a dielectric host. Okay. So, they are particularly important for low frequency regime than in the photonic crystal regime. So, in the low frequency regime, when the period is much smaller than the wavelength, such arrays can be called as wire media. As to the frequency range, where a wire medium becomes a metallic photonic crystal, they can be described as by set of pass bands and stop bands, and these are found applications at the microwave frequencies, right. So, very similar concept. You have TE and TM modes, or you can say E polarization or H polarization. These are like metallic media, metallic wire array. Okay. So, in the case of microwave electromagnetic bandgap structures, the wire diameters are typically in millimeter and sub-millimeter ranges, and if you go for optical domain, you will see that the optical wire media will be typically in nanometer dimensions. So, here is an example again. So, that shows the band structure of a photonic crystal comprised of square lattice of silicon rods in air, and you can see the electromagnetic band gap being shown in this case. Now, this band diagram shows only the main band gap. So, this we have seen earlier. So, a 3D photonic crystals without a complete band gap will look very analogous to metals. Those with narrow complete band gaps will be analogous to semiconductors, and those with a broad complete band gap will look like insulators, right? So this is how typically insulator will look like. You have a broad band gap, and narrow band gap will be typically like semiconductors, and then you have conductors with incomplete band gap or just no band gap. Now, this simplified band diagrams does not allow us to see the directional band gaps, and in general they do not tell us anything about the spatial dispersion, that is basically the relation between the eigenfrequencies and the wave vectors. So, the kind of band diagram I have shown you, that those are more comprehensive in its nature, and it tells you a much more deeper story, right. So, the spatial dispersion and the band structure of the photonic crystals, as I mentioned, should be always visualized in the Brillouin dispersion diagram. That means you should have the plot of the photon energy or the frequency versus the wave vector of the propagating eigenmodes. Okay. So, if you take an example, again a square lattice, this is how the Brillouin zone looks like, this is the irreducible Brillouin zone, and you have got the band gap, right. For a 3D structure also, you can think of a diamond lattice of holes being drilled. So, this is how the 3D Brillouin zone looks like, and this is how you can traverse around the irreducible Brillouin zone, right. So, you have to move across these different points of symmetry x, u, l, gamma, k, w. So, you can always look up to my other lectures in the previous course I floated. Okay. So, that tells you how these things are computed, but this is here just to tell you that for 3D variation of refractive index also, you can find out how the crystal will behave to a particular incident electromagnetic wave. If the wave falls within the band gap, it is not allowed to enter the crystal. If it is away from the band gap, yes, it can propagate or pass through the crystal, right. So, the band diagrams, as you have seen, are compact and almost incomplete, but you can say they do not have all the information, but they carry almost most of the information. So, you can characterize the electromagnetic properties of a periodic structure using band diagram, right. So, it essentially map the frequencies of the eigenmodes as a function of the block wave vector beta. So, this is how you can think of. So, you have got this particular periodic structure. So, this is the unit cell in 3D shown. So, you have got a wave with lambda, and the permittivity is here of the material is epsilon r. So, you basically need to solve this eigenvalue problem of the wave equation. So, del cross 1 by epsilon r del cross h equals k square h. So, here k square is basically for every block wave vector. Okay. So, this is basically the eigenvalue, and this is your eigenvector, right. I will range from 1 to infinity. So, once you solve this, you will get that beautiful band diagram, and it will tell you which are the allowed modes and which are not the allowed modes. So, we just put the two things side by side, the photonic crystal and your electronic crystals. You will see the similarity between them. Photonics, you have got, just if you take 1D, it is basically n high index waveguides. Okay. In solid state, you can also say it is a 1D photonic crystal of n atoms. Okay. Or it is not photonic crystal, it is like solid state crystals. There are different potential wells, so you can think of like that. Okay. So, this is how the analogy between the EK diagram looks like. Okay. On the right, you can see how the allowed bands and the band gaps are shown in the two cases, and you can also see that the field in the semiconductor and the photonic crystal, that can be written in similar form. You can also get the eigenvalue problem in the both cases. These are the operators. You solve for the eigenvalue equations, find out the solutions, and that will give you the band gap. So, it is very similar, and that is why the periodic media are called these are basically the semiconductors of light, right. So, with that we will stop this particular lecture. So, if you have got any query, you can always mention the lecture title and email to this particular email address. Thank you.